Okay, now let's move on to case 2. I would like to just remind you guys that in case 1, we actually established that Sn, so the terminal present value in the case of an annuity in arrear, has the following sum expression. So it's the sum of 1 plus I to the s power for s going from 1 up to n. For s going from 0 up to n minus 1. So let's just remember that for a second. Okay, great. Now let's get back to the case of case 2. In case 2, they say, let the contribution payment stream be an annuity due. They say, let C be this thing here, and that means we have n periods in our contract, but C now has payments at time 0, 1, 2, 3, 4, 5, and so on until time n minus 1. And what that means is all of the payments have been shifted 1 time unit forward. So they arrive in, if we have to interpret this, they would arrive in the beginning of the year instead of the end of the year. Now, what does that signify for our calculations? Well, first of all, if we just do the funny thing with the I at time n and think about how we accumulate all the earlier payments at time n now, then what we can see is, well, here I have 1 plus I to the first, right? And then I have, for n minus 2, I have 1 plus I to the second, and so on, until I have 1 plus I to the n minus first, and the payment that falls at time 0 has been accumulated all in all in time periods. So this sum, if I were to evaluate this sum in the same way that I did in case 1, well, I would have 1 plus I to the power s, but now we can see that s goes from 1 to n. And that is different from earlier, because what we had earlier was a sum where s went from 0 to n minus 1. So how does this sum relate to the sum that we had earlier? Well, the exercise actually wants us to show that in the case where the payments fall in the beginning of the time period instead of the end of the time period, then the accumulated value at time n, the terminal present value, is actually just the same as the terminal present value in the first case, but where we have accumulated each period's payment with another period of interest. So is that true? Well, it seems pretty likely, because all I see here is just, well, we just have to, what has been done is the same as the first case, except that everything gets accumulated 1 period more. So this seems intuitively very plausible. But let's try to show this, and also show this formula here, by going the strict mathematical route. So let's see. Math. Let's take a look at u of n by considering the formula from page 3 again. So I take the sum from time s up to time n, from the time s going from 0 all the way to n, for 1 plus I to the n minus s power multiplied by c of s. And then I notice when s is equal to n, there is no payment c. It's just 0. So, and for the other time points, it's equal to 1. So this sum is equal to the sum going from s equals 0 up to n minus 1. And then I have 1 plus I to the n minus s. And again, if I want to be able to use my geometric sum magic, then I kind of need to switch this up a little bit. So how do I do that? Well, what I can do here is I can say, let me see what happens. So when s is equal to 0, this thing up here is equal to n, right? When s is equal to 1, the power is n minus 1. And then n minus 2, n minus 3, etc. And all the way up to when s is equal to n minus 1, then what we have here would be n minus 1. And in that case, we would have the power 1 in the exponent. So that means I can change my index to, let's just call it k, where I let k go from 1, because that's the case when s is equal to n minus 1, and all the way until n. So 1 plus I to the s. No, sorry, to the k. Great. Okay, so now I've worked the summation index magic, and the next thing I want to do now is, well, just briefly note that the intuition part was right because the formula says so too. But then try to move on and show the stuff that we're asked to show up here. Well, one thing that could be really nice is if we already now can establish that this thing is equal to 1 plus I multiplied by Sn. So can we show this? And the answer is, well, yeah, it's not that hard to show. So how do we show that? Well, we want to show that this is equal to 1 plus I multiplied by this sum over here. And this sum has the indices 0, has the index s equals 0 all the way to n minus 1. So if I want to transform this sum into something that looks like this sum, then I need to do some more summation index magic. So let me try and see what we can figure out here. So one thing that could be nice is if I took out the 1 plus I, because that's where I want to arrive. I want to have 1 plus I outside of the sum. So let me try to take out 1 plus I. Then what's left inside the sum? Well, what's left here is 1 plus I to the k minus 1, because I've taken 1 outside the sum. I've taken 1 plus I outside the sum. And I still have the indices k equals 1 to n. Okay, but now what I notice is this. Inside the sum, the exponents are actually just 1 plus I to the 1 minus 1. So it's 1 plus I to the 0th. And then for k equals 2, it's 1 plus I to the 1st. And for k equals 3, it's 1 plus I to the 2nd. All the way up until k equals n, where it's 1 plus I to the n minus 1. So this sum is actually the same as the sum where I consider k going from 0 up to n minus 1. And then I just have 1 plus I to the k up here. Now this is a kind of like a standard summation trick that we can use always, which is that if I want to add something to the index inside the sum, then I just subtract that same number from the index here in the sum boundaries. So it's this kind of translation thing that we do, which is very nice. And it's a good trick to remember for later because it kind of turns up again and again. But then we actually have one of our results. It's that the terminal present value in the annuity due case is actually equals to 1 plus I multiplied by Sn. Okay, that's great, because maybe we can reach some of our other conclusions by using what we have here. So the other things we want to show is, well, respectively, that this 1 plus I multiplied by Sn is equal to 1 plus I to the nth minus 1 divided by d. And also we want to show that it's equal to 1 plus I to the nth multiplied by the initial present value of an annuity due. And well, how does that work out? It works out pretty great. To be honest, I don't even think that I actually need to go through this, so you can just stop the video now, because you just work from the 1 plus I Sn, and then you can reach both conclusions extremely fast. But there is a bonus video with the calculations after this one if you're interested anyways. Cheers!